All right, in this video, we're going to talk about a couple things. We're going to use two more of the gas laws, Dalton's law, and then a little bit later we'll talk about Henry's law. And we're going to use Dalton's law to explain the partial pressures of gases, especially oxygen, in the alveoli, at the respiratory membrane, at the alveolar surface. And the reason we have to talk about that is because we want to talk about delta P, right? And you should be thinking, he's talking about Fick, right? Because delta P is the pressure gradient for gases to diffuse. And of course, we're going to need gas diffusion across that respiratory membrane at the alveolus. And we need a driving force, a large delta P, to do that. So we really want to know what the alveolar partial pressure gases are so that we can assess whether or not we have decent diffusion, right? And so one thing we have to jump into here is the fact that in our hypothetical lung here, right, we are tidal ventilators. Right, tidal ventilation, we talked about this before, moving air in and out of a blind-ended bag as opposed to unidirectional ventilators like fish. Because of that, right, we have our PO2, P here stands for partial pressure, so it's the portion of air that is oxygen. We'll talk about that in a minute. So we have PO2 in air, and we have PO2 at the alveolus. And those two are not going to be the same because of this tidal ventilation, right? Because we're breathing each of our breaths into this blind-ended bag that already has some air in it, right? And so there's a dilution factor, again, which I've talked about previously. And so we can assess what portion of air is oxygen using Dalton's law, and then we can assess the PO2 of alveolar air using Dalton's law. Okay, so let's get into it. So Dalton's law basically says or states that the total pressure of a gas mixture, P total, equals the partial pressure of gas 1 plus the partial pressure of gas 2 plus the partial pressure of gas 3 plus so on and so on and so on for as many gases as we have. And air is certainly a complex mixture of gases. The good news is it's really made up of two main gases that make up 99.9% of the total pressure. And so if we say now we switch our P total to P atmospheric, we talk about air in our environment, it's really going to equal P nitrogen, partial pressure of nitrogen, plus the partial pressure of O2. And again, plus dot, dot, dot. But again, this dot, dot, dot is going to amount to very little. And we can go further and we can say that, all right, well, we know atmospheric pressure is about, at sea level at least, 760 millimeters of mercury. And we know that the fractional percentage, right? Now, this is not the partial pressure, but the fractional percentage, I'll write it below it here, of air that is nitrogen is about 79%, 0.79, and a fractional percentage that is oxygen is about 0.21. And again, if you add those together, you end up at 100%. So it's not quite, this one's actually slightly less than 21% because there is a little bit of the dot, dot, dot here, right? Carbon dioxide and carbon monoxide and methane and a million other gases. But we're close, right? And so if we take our 0.79 and then multiply by 760, we end up with about 600 millimeters of mercury. And of course, that leaves about 160 millimeters of mercury for the oxygen, right? So that is this, right? So, okay, so that's Dalton's law, and it explains how a gas mixture is comprised of individual gases, and that the total pressure of that gas mixture equals the partial pressures of each gas in it. Okay, so it's important because to determine our gradient down here, we have to sort of know what we're breathing in the first place. And one thing to point out is this 160 is not fixed, right? I said this is at sea level. If you go to altitude, well, it's not 760. It could be 660 or 600, right? In which case, it's still 79% and 21%. And so the 600 and 160, more focused on the 160 here, will fall, right? Which, of course, could change the alveolar PO2 as well. Like we could. I mean, we might compensate by hyperventilation and we might be able to maintain it. But if you go to too high an altitude, you can't. Now, if we look at another sort of way to state the outcome of Dalton's law here, is to say that the partial pressure of each gas, right, equals nRT divided by the volume, right? And we already know this, right? Boyle's law states that the pressure of a gas is inversely proportional to the volume. Here it is, right? But we also really want to know that the partial pressure of that gas is based upon the amount of the gas, right? That's the N is the molar amount. R is our ideal gas law. So that's our gas constant. Sorry, it's the gas constant in the ideal gas law. And T, of course, is temperature. Right? And this also makes sense because as temperature rises, air molecules or any gas molecules bang into each other more and would increase the pressure of the gas within a container. Right? If you heat up a balloon, that balloon will get larger, right? Because the air in it would be at higher pressure due to the thermal energy of the individual molecules. Okay, so there's Dalton's law. Now, what I want to do is go back to the slideshow for a minute and look and assess how Dalton's law is really, like, get at the details, right? Let's now look at the details of this. As soon as I'm able to escape. There we go. All right, so if we look at our slide here, right, we have our tidal ventilation. I pointed this out before. Get our pen moving here. Right, we talked about our tidal ventilation. And what I want to point out, right, and so here's our inhaled air, right? We were just talking about this a second ago, right? We've got our 160 and our 600, right? We just calculated those. And that's the air we'd be breathing into these alveoli. So the alveoli are here on the sides. Sandwiched in between are the capillaries, the pulmonary capillaries, okay? And so now if we look at alveolar air, though, look at this PO2. So sort of like this is that effect of tidal ventilation, right? Look, it's not 160, it's 105. And I usually even round that down and call it 100. And so again, that would be P1 in our delta P, right? Between air and blood, right? If you look at the PO2 in blood here, it's significantly lower. Well, guess what? This blood has been to your tissues, your systemic tissues, to deliver oxygen. And so the PO2 has fallen from this 105 down to somewhere between 20 and 40. Okay? There are other reasons besides this, just the dilution factor that this, we're at 105 instead of 160. And I don't want to get carried away with this, right? But a couple of those factors are, let me point to two things. When we use, here it is actually, right? When we do this calculation using Dalton's law for atmospheric air, we're assuming dry air, which means the partial pressure of H2O, vaporized water, is 0. Okay, right? Because 600 plus 160 equals 760, that's the total. When you inhale air, it becomes humidified. It is no longer dry air. And so now it's not 0, it's 47 millimeters of mercury. That's fully saturated air at body temperature. And so you have to subtract that from the 760, right? In addition, look at the PCO2. It's 40. There's no 40 over here in inhaled air. It's like 0.3 or something like that. It's really low, okay? So again, there are other gases that are taking up part of that total, which reduces the value of our alveolar PO2, okay? And again, minimizing, shrinking to a degree, our air to blood concentration gradient that drives diffusion. Okay, we have, just to point it out, we of course have to have an oppositely directed gradient, P1 to P2, for carbon dioxide, right? Our carbon dioxide here is 40 in the alveolar air. Remember, atmospheric is minuscule, but because we're not exhaling completely, it's much, much higher in the residual volumes of our lungs. But look at our pulmonary capillary blood, PCO2, 45. Aha. So a gradient, although a much smaller one, right? Instead of a 65 to 85 millimeter mercury gradient for oxygen, we have this 5 millimeter mercury gradient, 45 minus 40, right, for carbon dioxide. So you might think, wow, well, the gradient for carbon dioxide is really much, much smaller, and so diffusion's probably really not going to be very good for carbon dioxide. Except there's another factor. Now, that other factor is Henry's law. We have to bring in Henry's law to explain how gases move to and from solution. All right, so let's go backwards. Okay. And now let's talk a little bit about Henry's law. Henry's law can get really complicated, so we're going to keep it pretty darn simple. Henry's law explains there's lots of different ways to state it, but it states the relationship between the partial pressure of a gas and the concentration of that gas in a solution. So for instance, if we have a cup of water here, right, and we have particular gas molecules above that water, right? They're moving around, right? They're diffusing in space in 1,000 directions, right? But some of them will enter the solution, right? And that is going to be based upon their solubility, okay? And again, there's a couple different ways to look at this, but let's view it from the perspective of solubility first. And so Henry's law, when sort of assessing solubility, basically states that the solubility of a gas, Sg, is going to equal Henry's constant times the partial pressure of that gas. Right? So we can see as the partial pressure of the gas above that solution goes up, its solubility in solution rises. In other words, more molecules would move into solution. Right? Now, note, and that hopefully that makes perfect sense, right? The more of these molecules that I put here, let's think about that alveolar surface now with oxygen, right? If they think of this airspace as the alveolus, right, and this water down here as the cytoplasm of the cells or even the blood plasma, right? We need to diffuse that oxygen into solution, driven by the gradient, right? And the larger the partial pressure here, right, the more that gas will have a tendency to move into solution. Put a color arrow there. But you get the idea, right? Where we would start ending up with more of those molecules in solution. Now, again, the gradient becomes important because, if I have a lot of red guys down here, they're going to start diffusing out as backwards as well, right? And then you can have these counteracting diffusional, factors or magnitudes, right? Where one is essentially subtracted from the other, right? Anytime you have a gas in solution here and a gas in solution here, they are diffusing in both directions. It can be dominant, and that is the goal of ventilating the lungs, to keep the partial pressure of the oxygen high here in the alveolar air so that we maintain the gradient for diffusion in this direction. And remember, if this is not a cup but is in the blood, what are we doing with these molecules? Right? That blood is flowing. We're taking them away and replacing it with low O2 blood, right, that's coming in. Right? So we keep this low, maintain a high, relatively high, despite our tidal ventilation, O2 here, and of course, we get diffusion into solution. Right? So H, our Henry's constant here, is basically a measure that tells us how readily this gas, based upon its structure and the temperature and things like that, and even the solvent itself, how readily it will move into a particular solution. Okay, so go back to what we just said about oxygen and carbon dioxide gradients at the alveoli. Remember, the oxygen gradient was big, favoring movement into the blood. The carbon dioxide gradient was small, moving carbon dioxide out of the blood. But we need to move both of them fairly dramatically, right? Guess what? H is different for those two gases, right? Now another way to look at this, look at Henry's law, it's going to give us we use a different Henry's constant, right? But another way to write this is concentration of the gas is going to, in solution, so in water, right? Again, biological fluids we're talking about here, so it's in water, is going to equal the partial pressure of the gas divided by this thing called the volatility constant, K sub H. So H and K sub H are related, but they're kind of inverse, right? Because H is the tendency to move into solution, and KH is the volatility constant, a different way to sort of think about Henry's law. And so basically, it's a measure so volatility, right? That's a measure of how readily something comes out of solution, right? And so if you think about this equation, the concentration in solution is going to be related to the partial pressure of the gas. So that would be sort of your inward force, right? Divided by your volatility constant. Well, your volatility constant is talking about movement out of that solution, right? So the concentration in solution is really a ratio of how the driving force inward and the driving force outward, right? Hopefully that makes sense, right? The higher the inward force is, the higher your concentration will be, right? Directly proportional. Whereas the higher your outward force is, the greater your volatility, then the lower your concentration will be. Remember, inversely proportional. Guess what? Carbon dioxide has a much higher volatility constant than does oxygen, right? It has a much greater tendency to come out of water, okay? And so, because for carbon dioxide, right, the volatility constant is high, then the concentration will be low, meaning it will readily come out to reduce the concentration. You ready for this? This is why soda and beer is carbonated instead of oxygenated, right? You can use any gas to put bubbles into a drink, right? Some beers are nitrogenated. They use nitrogen gas, right? But it's easier to get carbon dioxide to move into and then out of, because of its high volatility constant, of a solution. right? And so you open that soda and pour it, right? Look at all those bubbles coming out, right? That's because of a very high volatility constant, as well as you had a lot of carbon dioxide in solution because of the high pressure. That sound you hear when you open a soda is basically 4 atmospheres worth of pure carbon dioxide leaking out of that headspace, that headspace above your soda, right? And all of a sudden, it's going to go from carbon dioxide molecules looking like this to basically none, right? Yet you have lots of carbon dioxide down here in your soda, and so what are they going to do? We have a gradient that's going to favor their movement out, right? So there's Henry's law helping us explain how solubility is greater in a solution when the partial pressure of the gas is greater, right? And so that helps oxygen. That's a good way to think of oxygen moving into solution because of the high partial pressure, right? And then in the second version of Henry's law, it kind of helps with the carbon dioxide explanation, I think. And you could use either equation for either gas, but I just think it helps with the logic of it because they're moving in different directions at the alveolar surface there, right? O2 is moving into solution, and CO2 is moving out of solution. And so if we use this second version of Henry's law down here, right, we can see that carbon dioxide, even though the partial pressure is relatively low, right, lower relative to compared to the oxygen, right, it has a high volatility constant. And because of that, because if this is high, that makes this low. And so our CO2, right, has this tendency to come out of solution even with a small driving force, right, that small delta P from blood to air. Okay, there's Dalton's law, there's Henry's law, explains the alveolar PO2, right, Dalton's law, and actually atmospheric PO2, right, and then Henry's law helps explain our gas exchange across the respiratory membrane, right? We have to have solubility and driving pressures to move these gases into and out of solution. All right.